Good morning, ladies and gentlemen. Thank you for being here with us for today's online event on harnessing the power of supercomputers to advance marine, offshore, and renewables, partnered with A*STAR's Institute of High Performance Computing. My name is Alethea from the National Supercomputing Centre Singapore, or NSCC for short. For those of you who are not familiar with us, NSCC is a national research infrastructure funded by the National Research Foundation of Singapore. NSCC is Singapore's first petascale supercomputer facility that provides high-performance computing and resources to all local research institutes, institutes of higher learning, government agencies, and companies in both the public and private sector. HPC resources are beneficial in a variety of ways in a number of different sectors. It enables research of the highest computational complexity and data intensiveness in areas like advanced modeling and simulation, artificial intelligence, and big data analytics to be completed in shorter time spans. If you are interested, do find out more about NSCC and HPC at www.nscc.sg. Continual development in high fidelity modeling and simulation allows scientists and engineers to derive deep insights from the detailed flow field information. This enables better evaluation and prediction of the performance, and devices optimized design for marine vessels and offshore platforms. Augmented by the power of supercomputing, the marine and offshore industry is now more receptive towards the idealization of digital twins and, in the near future, cyber-physical integration. Today's talk about harnessing the power of supercomputers to advance marine, offshore, and renewables will highlight the HPC applications in high-fidelity investigations, the development of digital twins, as well as new and innovative modeling and simulation technologies. Dr. Xiuqing is a senior scientist at A*STAR's Institute of High Performance Computing. She is experienced in computational fluid dynamics, optimization algorithms, hydrodynamics, aerodynamics, thermodynamics, fluid structure interaction, multi-phase flow, and underwater noise. Her research projects include digital twinning of tropical marine floating lab, CFD analysis on ballast water sedimentation, LNG boil-off rate determination and management, fully automated geometry modification and smart design, optimization process for ship hull form, enhancing offshore system productivity, integrity, and survivability in extreme environments. Before we get started with the talk, please do note that if you have any questions, do post them into the Q&A chat at the bottom of your screen so that Dr. Xiuqing can address and discuss this after the presentation. So without further ado, let me warmly welcome Dr. Xiuqing to get us started. Dr. Xiuqing, please.
Yeah, thank you, Alethea, for the introduction. Okay, good morning, everyone. Welcome to today's webinar. I'm very glad to have the chance to share something about the high-performance computing benefits to the marine, offshore, and renewables. I'm Xiuqing from IHPC. For those who are not familiar with IHPC, IHPC is an institute and A*STAR which aims to advance science, technology, and develop leading-edge applications through high-performance computing and computational science. We have 6 departments: fluid dynamic department, which is my department, electronics, photonics, engineering, mechanics, material science and chemistry, social and cognitive computing department, last but not least, computing science and AI department. So for our fluid dynamic department, from the name you can know, we are dealing with fluid flow related studies and research. We not only do research, we also do industry developments. So we have lots of collaborations with industry partners, from aerospace to marine offshore, food, semiconductor, and urban environmental, lots of projects. For marine and offshore side, from 2011, we have been actively working with local industry partners like Rolls-Royce Marine, Scotland Capo, Semcop Marine, Drone Port, and also the government agency, MPA, SMI, and class societies like LR, Class NK, ABS, DNV, GL, One of our projects was rewarded the best research project in 2016. High quality deliverables to our customer help us earn the trust from our partners. Now we have established a very strong relationship with our partners. Okay, back to our topic. Digitalization is a technology trend in these days. Everybody talking about digitalization, digital twins, as a model of your physical vessel. Digital twin provide every bit information for the physical models, from engine performance to the hull integrity. With the digital twin, operators can optimize their specified voyage in terms of fuel consumption and the time of arrival. So they also can make efficiency plans for their inspection and maintenance. So the industry taking the advantage of digitalization, move towards to green shipping and eventually to autonomous operations. So in this journey, what high performance computing can help? Here we're talking about the high performance computing. Actually, we are talking about computational fluid dynamics. So compared with the traditional model test or sea trials, the high performance CFD based Waterlab can provide access to all the fluid field variables, and also provide flexibility for your tank layout and experimental design. So it's not only help with the performance evaluation, so also help a lot for the design optimization. So for those who are not familiar with CFD, actually CFD use numerical analysis and data structures to analyze and solve problems that involve fluid flow. Here I quote Wikipedia. So normally we have 3 steps to do the CFD: pre-processing, solving, and post-processing steps. But in the pre-processing step, with your geometry, you need to define your domain and the condition that your boundary will not affect the flow, affect your flow inside your domain. So you also need to consider what the physical models involved in your problem. So according to that, to define your CFD model. And then we do the meshing to discretize your domain. After that, we solve our Gaussian equations. Basically, it's continuous equation and Navier-Stokes equation to get the information of your flow field as a pressure and velocity. So with the results, we can, at the post-processing step, we can visualize the results to help us understand the physical insight behind the flow. So normally this finishes our CFD procedure. But in order to get everybody have confidence to our results, we add one more step to validate and verificate our results by comparing with experimental data or analytical or empirical analysis. Just now I mentioned CFD-based Waterlab can help with performance evaluation as well as design optimization. So we developed our Waterlab starting from these 2 aspects. For the physical-based simulation side, we developed our tools for extreme wave generator for current wave interactions. We also developed near field, far field coupling models and dynamic meshing tools to improve the efficiency for complex problem simulations. We also developed tools to analyze the structural response with considering the morning dynamics. For the CFD-based design optimization side, we developed our code based on the current popular database design optimization methods, as well as the traditional optimization algorithms. So let's look at our Waterlab development. for the performance evaluations. Okay, the first tool I shared here is a wave generator. In the real sea, a lot of nonlinear phenomena we have to deal with, such as wave breaking, viscous drag, turbulence effects. All these are beyond the potential flow series measures capability. So CFD can handle this very well. So we develop a wave generator in our Waterlab. So with our code, we can generate waves according to wave series like Stokes, first order, second order, even fifth order series to generate regular waves. We also can generate waves according to Jones-Swap spectrum or PM spectrums for irregular waves. At the same time, our code also can generate waves according to the physical movement of pedals. Like the animation show here, actually it's a pedal generate waves. So we also can put the damping beach, similar as a physical tank beach damping zone. With this, you can see our simulation results match the experimental data quite well. The second tool I shared here is wave current interaction. We're starting from current and wave only. Sorry, excuse me. For the current only case, we capture the mean velocity of the current, and with different methods, we can also capture the turbulence kinetic energy profile of the current. For the wave only case, we capture the wave profiles. We try to minimize the decrease with the wave propagation. We make sure our profile can keep quite well after certain wave period. So for the wave current interaction, you can see when they have interaction, the current profile and the wave profile changes a lot. When the wave met a following current, the wave will display a sharper crest and flatter trough. So when the wave met opposite current, the wave period will become shorter, and the waves normally will pair up each other and even induce form an extreme wave or induce wave breaking. Our code can handle this kind of problems. Okay, for those have structures in waves, the problem becomes very complex. We need to deal with incident waves. We also need to deal with disturbed waves around the bodies. For this one, because the incident waves requires quite large domain, and the disturbed waves requires for fine mesh around the body to capture the turbulence and wave breaking cases. So all this one will increase our computational costs in terms of computational time and computational resources. Even we have NSCC's supercomputers help, we need to do our work smartly. We cannot, don't consider our cost and do it. So we need to find a smart way. So we are thinking, why don't we couple the potential flow and CFD flow together to improve the efficiency? For the far field waves, where the waves linearity can be justified. So we can use potential flow to simulate it. For the near field part, we have to use CFD with fine mesh. So we couple them together, and at the interface zone, the buffer zone, we use interpolation to exchange information between these two methods. So with the barge case as the example, we can generate the incident wave using moving pedals. Then far field, we use potential flow to capture the waves. Near field, we use CFD to do the simulations. We can see our simulation results match the experimental data quite well. Okay, just now I shared a case for coupling the two measures, CFD and potential flow measures. We still have a lot of complex problem to handle. For the structures inside the domain have movement, they travel across a long distance problems. We cannot keep a large domain to simulate the case. So CFD scientists developed this offset mesh method for the case with for the ships with a rotating propeller, for the launching of torpedo anchor, or the launching of left boat from platform. We can use this method. With the sphere in water, drop to the water surface as an example, we can see we have our background mesh. We have a mesh around the body. The offset mesh all the way follow the body to move. So we no need to regenerate any mesh. We no need a very big domain to capture the whole phenomena. So in this way, we only interchange information at the interface of these two meshes. A couple of years ago, my colleague Dominic developed this offset mesh for the open source CFD software OpenForm. The development earned recognition from the OpenForm Society. So we filed a TD for this development. Currently, for the normal CFD, the commercial CFD software like StarCCM, Fluent, all have this kind of functions. It's quite convenient to deal with the motions, relative motions of structures. Okay, another tool we developed is for the structure in current. It seems simple, but for structure in current, when the current flows through the structures like semi-submersible, it always have vortex shading behind the structure. The shading vortex will induce motion of the structures. We call it VAM. So for this case, we use large ID simulation to capture the VAM. After validate our model, we use it to find a passive control method for the VAM. Our simulation found tested column will have depressed the VAM. So this result shows for this case, particular case, our simulation results shows we can reduce 90% VAM at the peak lock-in conditions. Okay, with our code, we also can capture the wave profiles, wave breaking. At the same time, we can monitor the force on the structure, the wave load on the structure. We still have a lot of tools and examples, so I'm not share it here due to the time limitation. Now let's look at the design optimization tool development. Traditional CFD-based design optimization, starting with the initial shape, use CFD to get the objective functions. Then according to the design criteria to decide whether your criteria is satisfied or not. If not, use optimization methods to determine the changing directions to find a new shape and go back to next loop. There are lots of design optimization methods. Each of them has its own advantage and disadvantage. Like gradient-based methods, their efficiency is high. They are easily to apply to all size, shapes, and topological designs, but they cannot be used for discontinuous functions. Stochastic methods are numerical network methods, and they can be used for any functions, complex problems, but normally they take more iterations to get the optimum. so the efficiency is not so high. So currently, the database methods and machine learning methods are quite popular. So people are looking at circuit-based algorithms. For CFD, we know given the initial and boundary conditions, we are using full order models to get the objective functions. For circuit models, people are trying to reduce the order or use simple methods to get the objective function to improve the simulation efficiency. We can categorize the circuit models into three types: data fit circuits, multi-fidelity circuits, and reduced order circuits. Database circuits, basically they build up a database. You either use CFD or experimental data. From the database, they build up their response surface, and on that surface to find out the optimum. So it has a high speed up, but must balance local consistency with global accuracy. For fidelity, excuse me, for multiple fidelity circuits, we are using causal mesh to improve the computational efficiency. So efficiency is not so high. Reduced order circuits is emerging methods. Basically, it's found a single value decomposition to project the function from a full order space to a reduced order space. It's quite promising, but still need further development for nonlinear dynamic systems. Okay, with the circuit models, the design optimization problem becomes like this. From your initial design, you define your design space. Within your design space, to design your experiments, to form the DOE, use CFD to collect the objective functions. Of course, here we're talking about CFD-based methods. So if you have experimental data, you can also use that one to build up your database. So from here, to build up the circuit models and you, according to the circuit model occurrency, to decide whether you go further to optimization or you go back to increase your DOE. If the circuit model accuracy is high enough, you go to the optimization part side and say check whether your target achieved or not. If not, you reject the optimum samples back to the DOE. With your DOE data increase, of course, your covered range will increase. So it can go nearer to the optimum points. Okay, the design optimization methods we have already. Evaluation for performance we also have. So we are considering develop a platform which is user-friendly and has high efficiency for industrial applications. So smart platform requires for automatic analysis for the performance evaluation to improve the efficiency. And it also requires for design optimization methods to reduce the dependency on designers' experience. So with this, we can get innovative designs. But when we develop our platform, we found there's still a gap between the design model and the automatic analysis. What is it? So because the designer, they only care about the shapes, the dimensions of their design. They only tell the manufacturer or what the shape looks like, how to generate it, and what the dimension is. But as safety engineer or scientist, we care about the geometry, whether it's watertight or not. If it's not watertight, the fluid flow will go into the structure, which is not the real case. So every time we get the model from designer, we found there are lots of problems. The small gaps, holes, overlap surfaces. So we need to fix this one. Normally, for simple case, we may take days. For very complex case, like the FPSO topside or jack-up topside structures, it's very complex. It even takes weeks. So this is not, we don't like. So we consider we have modeling, geometry modeling experts. So why we go backward one step, we're starting from the raw offset data, regenerate the structures, and form our watertight geometry model. So currently, this step we have been finished, and we developed a platform. Currently, this platform is not included in the design optimization part. It's from the offset data all the way to the performance analysis. The user only need to provide the offset data, click on the geometry generating pattern, provide the hull dimensions and operation conditions, and can do the computational computation and do the visualization to check the results. Right? This one is not only design tools for industrial applications. It also can be used as teaching tools. This one was tested by SIT final year students. They found it's quite user-friendly and efficiency is very high. It can help the students to understand the CFD procedures and how to do the hull performance evaluations. Okay, let's look at our Waterlab's application in grain shaping and digital twins. So IMO already set a target by 2050. They will cut the greenhouse gas emission at least 50% compared with that in year 2008. So this target, we need to reduce, we need to optimize the hull performance, reduce the resistance, increase efficiency to reduce energy consumption and further reduce the green gas emissions. So our tools can help to evaluate the hull resistance, either cup water resistance or wave-induced ideal resistance. Our tool also can help you to get the water elevation along the hull, so you can use it to do the green water risk assessment. Again, for CFD, you can either do the model scale simulation or in full scale simulation. So it can provide access to all field variables and provide flexible in operational conditions. Is this like this? We can provide the pressure distribution on the hull surface. So with the pressure information, you can do the global structure or local structure analysis for your hulking, sacking, or with the impact load analysis. Improved efficiency is a good thing, but it's not always leading to good results. Like propeller, increasing demanding for the efficiency of propeller drives it to the situation of in the normal operations, the surface ship cannot avoid cavitation. We know cavitation has a lot of problems. It produces vibrations, noise. It will accelerate the wear of the components like the rudder, the bear shaft. It also causes blade erosion and consequently corrosion and damage the blade. So we need to consider how to balance the efficiency and the cavitation. For CFD, we can use offset mesh to capture the rotating of the propeller. We can capture the cavitation volume in the one circle. And we can capture the reception points and vantage points of the cubitation. At the same time, we can get the pressure on the hull surface. With the pressure information, can do the vibration and noise analysis. AMO, the target for greenhouse gas emission target, it also drives the operator to consider transit away from high pollution, high polluting fossil fuels. So LNG as a cleaner fuel, lots of people are exploring it as a fuel. But for LNG, you have to deal with the bore-off problem, because bore-off happens at any time, any stage of the whole supply chain, from storage, transportation to the bunkering procedure. As long as there are heat ingression and pressure change in the tank, makes the temperature higher than the boiling point of LNG, the bore-off will happens. So according to the excess temperature, the bore-off phenomena happens in 3 stages. Either it's nuclearic boiling or transit boiling, or is totally separated 2-phase flow boiling. So for CFD, we have three kind of models according to the boiling types, so it can handle this problem very well. At the same time, CFD is not only consider the heat conduction, we can also consider the heat convection due to the fluid flow inside the tank. So for this case is a C tank. We can see through our simulation, you can see when the heat goes into the tank, the liquid near to the wall will get warm, again heat and get warm. It will become light and it goes up to the surface. At the surface, evaporation happens, take away the heat, and the liquid becomes cooler. At the center part, it goes down. So with CFD, we can also do the parametric studies to help us to understand environmental temperatures effect, the pressure inside the tanks, the pressures effect, and the filling levels effect. So help the industry to understand better what happens and what the key factors. So IMO not only set target for greenhouse gas emission, they also have developed regulations for the ballast water management to protect our environment. So with our code, we can help to monitor the movement and distribution of the sediments inside the ballast water tank. Can help the operator to make a plan, make a cleaning plan, and find out a feasible and practical cleaning measures. So we can also do parametric studies about the deballast pad positions, lightning hole size, position, numbers, and the Belmos locations, particle size, water jet pressure, and temperatures, and so on. All these parametric studies can help the designer to design their ballast tank or make modification to their current tank to achieve a better ballast water management. Okay, lots of cases will not share here due to the time limitation. So we look at the Waterlab applications in offshore renewable energy part. So offshore renewable energies collection currently mainly from offshore wind, waves, and tidal current. So for tidal turbine, our code can help not only for the design, for the performance evaluation at design operation conditions, it's also for off design conditions. Like this, we use MRF mesh to capture the motion, the rotating of the blades. Near the blade surface, we need fine mesh to capture the feature line of the blades. Otherwise, it will affect the accuracy of your results. This case is a misaligned case. The current is misaligned with the tidal turbine shaft by a 30-degree angle. So you can see our results is quite clear for us, for the industry to understand this, what happens, what the flow field looks like. At the same time, we also care about the weak flow behind the turbine. Why? Because when you design your turbine farm, you need to understand where to put your turbine on the downstream. You cannot put it under the previous weak zone. It will definitely affect the performance of your turbine. So for floating wind turbine case is very challenging. You need to consider aerodynamic of the wind turbine. You need to consider the hydrodynamic of your floater. At the same time, the floater bobbing on the water surface will definitely affect the aerodynamic of your wind turbine and affect the power collection capability of it. We also need to consider the morning line effect on the motion of the floater. So it's very complex. Thanks to NSCC, because the supercomputer provide us the capability to capture all this together, to capture this phenomena. We can couple all these effects together. So you can see with the CFD simulation, we capture the pitch angles, the wicks from the blades. It's very clear what happens in the flow field. This case is a 5 megawatt wind turbine because we don't have experimental data available so far. So we compared with others published data. So you can see the models match quite well with each other. Okay, with this, I summarize my presentation here. So high performance computing will definitely benefit to marine offshore industry and offshore renewable energy sectors, make the performance prediction and design optimization more efficient. It will help the industry move towards green shipping, digital twin, and lead to autonomous operation eventually. Here, I would like to thank my IHPC colleagues, Dr. Lo Jing and Dr. Chang Wei, for their planning for the Waterlab development. I also would like my other colleagues listed here for the development of the Waterlab. I also would like to thank National Supercomputing Centers and NSCC for them to provide this chance for us to share our experience here. Now I would like to take your questions.
Okay, thank you, Dr. Xiuqing, for the great and insightful sharing. We have one question. Are you currently working with anyone to develop floating wind or tidal turbine in Singapore?
Yes, but I cannot release more because currently it's still considered as confidential information.
Okay, sure, got it. All right. I think that's all the questions that we have for today. Dr. Xiuqing has shared her email address in the slides. So do feel free to get connected with her after this session should you have any questions that you would like to ask her after this. Also, the recording of this session will be uploaded on NSCC's YouTube channel. So do head there for a review of today's event. So that concludes NSCC's first webinar series on supercomputing, powering a smart digital nation. Do keep an eye out for the next series of webinars that we are planning. Details will be posted on our website and social media channels. So we'll see you at our next online event. Bye.
Bye.